A computer's hardware, on its own, is just a collection of inert silicon and metal. To actually do anything useful, those physical components need precise step-by-step instructions. We usually start by loading an operating system. This system software manages the memory, the processors, and the devices, keeping the machine running smoothly. But an operating system alone won't write an essay, balance a spreadsheet, or edit a video. That is where application software comes in. It sits at the top of the stack, bridging the gap between the operating system and you, the user, providing the specific tools needed to accomplish real-world tasks. Ultimately, the entire architecture of a computer system exists to support this top layer. Generating and running these applications is how we turn machine execution into human solutions. When we talk about applications, we are talking about software built entirely around the human user's needs. Whether it is a word processor or a complex CAD/CAM system for designing physical products, its goal is to help a person complete a specific project. This flowchart shows the formal hierarchy of software, separating applications on the right from system software on the left. Following the left branch down, we find utility programs. These maintain the computer's internal operation, rather than serving external projects. Compressing a file or running an antivirus scan are utility tasks. They keep the system healthy and efficient. Designing a car engine, on the other hand, is an application task. So if you need to categorize a piece of software, look at its primary beneficiary. If it serves the user's goals, it is an application. If it serves the machine's needs, it is system or utility software. For decades, the standard way to distribute software was as a closed source or proprietary product. The original code written by the developers is hidden from the public, meaning only the owning company can authorize updates or fix bugs. Open source software takes the exact opposite approach. A common mistake is thinking open simply means free of charge. What it actually describes is the visibility and availability of the source code itself. This text outlines the core philosophy of open source licenses, like the GNU General Public License. It guarantees the user's freedom to inspect the code, modify it to suit their own needs, and redistribute those changes. This creates two very different ecosystems. Closed-source software typically comes with dedicated professional support and guaranteed security patches from the manufacturer. Open source relies on a distributed community of independent developers to audit the code, find vulnerabilities, and build fixes together. The developer's choice of license dictates everything about the software's future. It determines how transparent the code is, how heavily it can be customized, and who ultimately controls the development roadmap over time. Whether open or closed source, humans write applications in high-level programming languages like Python or C++. Processors cannot understand these languages directly. The code must be translated into binary machine code before the CPU can execute a single instruction. A compiler takes the entire batch of source code and translates it all at once, outputting a standalone executable file. This compiled file runs incredibly quickly and strips away the readable code, protecting intellectual property for commercial software. An interpreter handles the job completely differently. Instead of creating a finished file beforehand, it translates and executes the source code line by line while the program is actively running. No executable file is ever saved. This table shows a direct comparison. Compilers prioritize execution speed and intellectual property protection, distributing a hidden executable. Interpreters require the source code to be distributed, putting IP at risk, but make cross-platform testing and debugging much easier. There is also a third type of translator, called an assembler. Rather than handling high-level languages, an assembler translates low-level assembly language, which uses short English mnemonics like add or load, directly into machine code binary. Selecting a translator is always a strategic choice. A developer must balance the efficiency of the final hardware execution against their own productivity during coding and the need to keep their intellectual property secure. Let's review a few key traps to avoid on the exam. Remember that utilities are strictly a subcategory of system software, not applications. And open source refers to the legal right to view and modify the code, not whether the software is free to download. Also, keep in mind that interpreters must retranslate the source code every single time the program runs. And assembly language is not high level. It is simply a mnemonic-based layer just one step above raw machine code. High-level languages, whether compiled or interpreted, have a one-to-many mapping, where a single line of code becomes many machine instructions. Assembly language, translated by an assembler, is strictly a one-to-one mapping. To tie it all together, you have hardware at the base, managed by system and utility software, supporting the applications humans actually use. And to bridge the gap between those human-readable applications and the hardware, we rely on compilers, interpreters, and assemblers to make the code execute.